In this video, I'll be finding the derivative of several functions involving logarithms, specifically natural logs. So our first function, we have y equals x minus the natural log of 4x. And so to find our derivative, dy dx, we take the derivative of each term. The derivative of x is just 1. And then the derivative of the natural log of something is just 1 over that something, in this case 4x, times the derivative of that argument. So the derivative, in this case, of 4x, which is just 4, so we get 1 minus 1 over 4x times 4, which is just 1 minus 1 over x. And this is going to come up several times, so we can actually show that the derivative with respect to x of the natural log of any number, so I'll call it some number c times x, we can show that this is going to equal 1 over x. So if we let u equal cx, and that's going to make this ln of u, then to get d by dx, we'll have to imply the chain rule. So this will be d by du times du dx. So the derivative of natural log of u with respect to u is just 1 over u, and then times du dx, which is just c. But when we plug back in for u, we will get 1 over cx times c, which is just 1 over x. So we can show that no matter what constant is in front of x, our derivative of the natural log will just be 1 over x. And we'll use this from time to time. Okay, our next function, we have y equals 3 over the natural log of 4x. So the first thing I can do is rewrite this as 3 times the natural log of 4x raised to the minus 1. And then I can write this doing a u substitution by writing this as 3 times u to the minus 1, where u is the natural log of 4x. And now I can just apply the chain rule. So to get my derivative dy dx, I need to take the derivative dy du times the derivative du dx. So for dy du, I will bring down my minus 1. So I'll keep my 3 out front, bring down my minus 1, and then lower my exponent to a minus 2. And then I need to take the derivative of u with respect to x, but we just found that that's just going to be 1 over x. And so now if I plug back in for u in here, I will get minus 3 over x times u. My u is going to be squared on bottom since it's negative, and that is ln of 4x all squared. Okay, the next problem, we have y equals the square root of x plus the natural log of x to the 5/2 power. So the first thing I want to do is rewrite this. Rewrite my radical as a fractional exponent. And then I want to use the properties of logarithms to bring this 5/2 down. So anytime you have the natural log of something raised to a power, you can bring that power out front, just like this. And now I can take the derivative with respect to x of each term. So I'll bring down a half for my first term, and then I'll need to lower that by 1, so it'll go to minus 1/2. And then plus my 5/2 constant will come out front. And then the derivative of natural log of x is just 1 over x. So now I just need to simplify a bit. So I can write this as 1 over 2 times the square root of x plus 5 over 2x. Okay. And if I wanted, I could factor out a 1/2. And then I could multiply this first term times the square root of x over the square root of x. So just multiplying by 1. And that would give me a common denominator of x after I factor out my 1/2. So now I can combine these and write this as square root of x plus 5 all over 2x. Next function, we have y equals the natural log of theta cubed plus the natural log of sine theta. So the first thing I want to do is use my properties of natural logs to rewrite this first term as 3 natural log of theta. And my second term will stay the same. And now I'm ready to take the derivative. So the 3 will stay out front. And the natural log of anything is just 1 over that thing. So in this case, theta. Plus, in this case, I'll do the exact same thing. So 1 over the argument of natural log, which is sine theta, times the derivative of sine theta, which is just cosine theta. And then I can simplify this. Cosine over sine is just cotangent. So I have 3 over theta plus cotangent of theta. In the next function, we have y equals sin x times the natural log of 3x plus 4. So this is going to be a product rule. So I want to let u be my first function, sin x, and v be my second function, the natural log of 3x plus 4. Then my u prime will be cosine of x, and my v prime will be 1 over the argument, 3x plus 4, times the derivative, which is just 3, or 3 over 3x plus 4. And now, to get my derivative, I'll just plug into my product rule. So the derivative of the first times the second, plus the first times the derivative of the second. And I will get u prime, which is cosine x, times v, which is the natural log of 3x plus 4, plus u, which is sin x, times v prime, which is 3 over 3x plus 4. And so I can simplify that last piece just a bit by writing 3 sin x over 3x plus 4. Okay, for the next two functions, we have y equals the natural log of t cubed, and then we have the natural log of t all quantity cubed. So in this case, we have only the t being cubed, and then we're taking the natural log. And in this case, we're taking the natural log of t and then cubing that result. So I want to show that both of these give different derivatives. So you have to be careful and make sure that you don't treat these as the same thing. So for the first one, we want to use the properties of logarithms. The natural log of something raised to some power is just that power coming out front times the natural log of the original argument. So now if I take the derivative of this, dy dt, I get just 3 times the derivative of the natural log, which is 1 over t, or 3 over t. For the second one, I can't use the properties of logarithms because the argument itself isn't what's being cubed, it's the entire natural log. So I need to write this as a function u cubed, where my u is the natural log of t, and then I'll need to do the chain rule. So dy dt will just be dy du times du dt. And so dy du will just be 3u squared times du dt, the natural log of t, that's just 1 over t. And then when I plug back in for my u squared, I get 3 times the natural log of t all squared over t. So these are very different, so make sure that you pay attention to where your exponent is in respect to your natural log. In the next problem, we have y equals 2x times the natural log of the cube root of x. So I first want to rewrite this a bit. So this is going to be 2x times the natural log of x raised to the 1/3 power. Well, now that this is the natural log of x to some power, I can bring it out in front using the properties of logarithms. So this is going to be 2x times 1/3 ln x. And now I have two functions of x, so I'm going to have to do a chain rule to take a product rule, sorry, to find the derivative. So dy dx is going to be u prime v plus uv prime. So the derivative first times the second plus the first times the derivative of the second. So here my u is going to be 2x, and my v is going to be 1/3 ln x. If you wanted, you could factor out these constants. I'm just going to leave them there. U prime is going to be 2, and v prime is going to be 1/3 times 1 over x, or 1 over 3x. And so now I can just plug in. I have 2, which is my u prime, times v, which is 1/3 ln x, plus u, which is 2x, times v prime, which is 1 over 3x. And bringing this together, I have 2/3 ln x plus, our x's are going to cancel, and we get 2 over 3. And if you wanted, you could pull out this 2/3 and get 2/3 ln x plus 1. The next function, we have y equals, in parentheses, t cubed times the natural log of t, all squared. It's a quantity squared. So the first thing I want to do is I want to take this square and distribute it to simplify this a bit, to keep from using the product rule inside of a chain rule. And so by distributing this, I multiply the exponents. So an exponent raised to an exponent is just the product of exponents. So this is t to the 6th times the natural log of t all squared. So now I have my two functions of t, and I need to use a product rule. So my first function will be t to the 6th. My second function will be the natural log of t squared. So u prime will be 6t to the 5th. And v prime, I'm going to have to use the chain rule here, but it's a little bit easier. So it's just going to be the derivative of the outside. So I'll bring down my 2 and lower that to 1, and then multiply by the derivative of the inside, which is natural log of t. So the derivative of natural log of t is just 1 over t. So v prime is 2 natural log of t over t. And now my dy dt will be u prime v plus uv prime, or my u prime is 6t to the 5th times v, which is the natural log of t all squared, plus u, which is t to the 6th, times v prime, which is 2 ln of t all over t. Okay, so we can simplify this a bit. So I'll just rewrite this first term, 6t to the 5th natural log of t squared, plus one of these t's are going to cancel, and we get 2t to the 5th times natural log of t. And now we can factor out a 2t to the 5th natural log t from both terms. And then that'll be multiplying 3 natural log of t plus 1. In our next function, we have y equals 2t times the natural log of t all over the natural log of t plus 3. So this is going to be a quotient rule. And so I'm going to let first function be 2t natural log of t. So this is going to involve a product rule when we find u prime, but it's really not that bad. And then v is going to be my lower function, or natural log of t plus 3. So my u prime is going to be the derivative of the first function, which is just 2t, so it's going to be 2 times the second, ln of t, plus the first, 2t, times the derivative of the second, which is just 1 over t. So when I simplify that, I get 2 ln of t plus 2. Okay, so if you need to do that out and take your time, that's perfectly fine. But you get kind of comfortable with the product rule and it's not too bad. And then v prime, the derivative of v is just going to be 1 over t. And so now my derivative of y with respect to t will be low d high minus high d low all over low squared. So v is going to be ln of t plus 3 times u prime, which is 2 ln of t plus 2, minus u, which is 2t natural log of t, times v prime, which is 1 over t, all over v squared, which is the natural log of t plus 3, all squared. Now if I distribute this out, I get 2 times the natural log of t squared plus, that's this term, plus 2 times the natural log of t, so that's this term. And then I'll do this term and this term, so that will be plus 6 ln of t plus 6, and then minus the t's on this right hand term are going to cancel, and I'll just have 2 ln of t. These are going to go away, and then I still have my denominator, natural log of t plus 3 all squared. And now if I want, I can factor out a 2 from each term on top. So I will get 2 times the natural log of t squared plus 3 ln of t plus 3 all over the natural log of t plus 3 squared. Okay, our next function, we have y equals the natural log of the natural log of the natural log of x. So to do this, we're going to have to be a little careful. So first I want to write this as the natural log of some function u. So maybe I'll put that in parentheses. In order to do that, u will have to be the natural log of the natural log of x. But I want to do this again, so I'm going to do kind of a nested chain rule. I'm going to do the chain rule again. So I want to write u as the natural log of some function v, and so for that I need v to be the natural log of x. So now if I want to get dy dx, I need to do the chain rule, but this time with 3 terms. So I need to first take the derivative of y with respect to u, and then multiply by the derivative of u with respect to v, and then multiply by the derivative of v with respect to x. And you can kind of see my du's are going to cancel and my dv's will cancel, leaving me with just dy and dx, which is what I'm looking for. So if I do this, dy du, just right here, is the derivative of the natural log of u, which is 1 over u, times du dv. So I'm going to look at this. Well, the derivative of the natural log of v is just 1 over v. And then dv dx, I'll look at this, which is, we'll just take the derivative of the natural log of x, which is just 1 over x. And so now all I have to do is go back and plug in my u and my v. So u will be, so this will be 1 over u, or 1 over natural log of x, times 1 over v, which is the natural log of x, times 1 over x. So we can simplify by just having 1 over x times natural log of x times the natural log of the natural log of x. In this next function, we have y equals 2 plus ln of x all over 2 minus ln of x. So this is going to be a quotient rule. So we need our top function to be 2 plus ln of x, and our bottom function to be 2 minus ln of x. So our u prime is going to be 1 over x, and our v prime is going to be minus 1 over x. okay, just by taking the derivatives of natural log. So dy dx is going to be low d high minus high d low over low squared. So our function v is going to be 2 minus ln x times u prime, which is 1 over x, minus u, which is 2 plus ln x, times v prime, or minus 1 over x, all over v squared, which is going to be 2 minus ln of x squared. Okay, so if we pull these together, both of these terms on top have a 1 over x. And so I can actually just move that down, and I'll have 2 minus ln of x plus 2 plus ln of x. Okay, so that's those minus signs canceling out. And then I have 2 minus ln of x squared, and my x on bottom that I got from both of these terms. Okay, and then I have a minus ln of x here and a plus ln of x here. And then I have a 2 and a 2 that are going to add to give me 4. And so I'll be left with 4 over x times 2 minus ln of x all squared. In our next function, we have y equals the natural log of 1 plus 3 times ln of x all over the square root of cosine x sin x. Okay, so we're going to need to rewrite this a few different times just to simplify it, where it's much easier to take the derivative. So the first thing I want to do is notice this is the natural log of a quotient. That means I can write it as the natural log of the numerator minus the natural log of the denominator. So square root of cosine x sin x. Okay, now I can write this second piece as something to a power. So this is going to be cosine x sin x raised to the 1/2 power. And now I can use the properties of logarithms to bring that in front. So this is going to be minus 1/2 the natural log of cosine times sine. But this again is, I'm going to rewrite it over here. Now I have the natural log of a product of two things. So if you want to combine some of these steps, you're welcome to do that. But I'm just trying to make sure I don't miss anything. So this 1/2 is going to multiply everything in here. So this is going to be natural log of cosine plus the natural log of sine. Okay, and now I'm ready to take my derivative. So the derivative of the first term is just 1 over everything in the argument of the natural log, or 1 over 1 plus 3 ln of x, times the derivative of the inside. Well, that's just going to be 3 times 1 over x, minus, so maybe I'll put that in parentheses, the derivative, so minus 1/2 of the derivative of the second term. So again, it's going to be 1 over the argument of the natural log times the derivative of that argument. So this is going to be minus sin x, plus, again, 1 over the argument sin x times the derivative of the argument cosine x. And so now we just have some cleaning up to do. We have 3 that's going to be on the top over here. And then this x, so this is our 3 on top, and this x is going to multiply everything in the numerator of this very far left term. And then we'll have plus 1/2. I'm going to factor out this minus sign and write this as 1/2 tangent of x. So minus and minus will be plus, and then the second term will be minus, and cosine over sine is just cotangent x. And if you wanted, you could distribute this x on bottom. You could also, if you wanted to pull this 3 out into your logarithm, you could do that. But otherwise, this is what you get. Okay, our next function, we have y equals the natural log of t cubed minus 2 all to the 4th power, all divided by the square root of 3 minus t. So as always, we want to rewrite this so we have the natural log of a quotient. So we can write that as the natural log of the numerator minus the natural log of the denominator. And I'm going to go ahead and write this to the 1/2 power. So now we can use our property of natural logs to bring our exponents out in front of our natural log. Like that. And now we can take the derivative fairly easily. So for this first term, we have our 4 that comes out front. Then we take the derivative of the natural log, which is just 1 over the argument, times the derivative of the argument. So this will be 3t squared. Then we do the same thing with the next term. So 1/2 comes out front, times 1 over the argument, times the derivative of the argument, which is just minus 1. And then bringing this together, we have 3 times 4, which will give us 12t squared, all over t cubed minus 2. And then on the other side, we have a minus and a minus, which will make this plus 1 over, we could distribute this 2 and make it 6 minus 2t. The next function, we have y equals the natural log of sin²x. So this is the same thing as natural log of sinx squared. So again, only the sine is being squared. And so we can use the property of logs to bring this out front and just get 2 times the natural log of sin x. Now that's pretty easy to take the derivative of. So now we just have our 2 that comes out front. The derivative of the natural log of sin x, we just bring the argument to the bottom, sin x, and then multiply by the derivative of sin x, which is cosine x. But cosine x over sin x is just cotangent, so we get 2 times cotangent of x. The next function, we have y equals the natural log of 3 times e to the minus x times cosine x. So here we have natural log of a product, so we can write this as the natural log of all of these things added together. So first we have natural log of 3 plus the natural log of e to the minus x plus the natural log of cosine of x. So all these things are being multiplied, so we can separate them and take the natural log of, or the sum of the natural logs of each individual function. So we will get natural log of 3, and I'm going to bring this exponent minus x out in front and get the natural log of e, which is just going to go to 1, plus the natural log of cosine of x. Okay, so now if I take the derivative, the natural log of 3 is just a number, so the derivative is just 0. And then the natural log of e, this is just 1. So it's really just the derivative of minus x, which is minus 1, plus the derivative of natural log of cosine, which is 1 over cosine, times its derivative, which is minus sine. So if we bring all that together, we have minus signs for both of these, and then 1 plus sine over cosine is tangent of x. So that's what we get. Okay, for our last function, we have y equals e to the minus cosine x times the natural log of x squared plus 1. So the first thing I want to do is rewrite this just a little bit. E to the minus cosine x times 2 natural log of x plus 1, just bring our 2 out front. And then this is going to be a product rule. So our first function will be e to the minus cosine x, and v will be 2 ln of x plus 1. So for our u prime, we have e to the minus cosine x. This is just going to be minus e to the minus cosine x times the derivative of cosine x, which is minus sin x. Or our minus signs are going to cancel, and we'll get e to the minus cosine x times sin x. So if you need to do that separately somewhere else, you can, and see that it equals this. You can just do a simple u substitution and use your chain rule. And then v prime is just going to be 2 times 1 over x, or 2 over x. And so now we can do the derivative dy dx as the derivative of the first times the second plus the first times the derivative of the second. And so u prime will be our e to the minus cosine x sin x times v, which is 2 ln x plus 1, plus u, which is e to the minus cosine x, times v prime, which is 2 over x. And then we can just substitute just a bit. Both of these have an e to the minus cosine x. Then we have sin x times 2. Actually, I'm going to go ahead and bring this in. Natural log of x squared. So now I'm going to go the other way and bring the number out front in as an exponent to the argument of the natural log, plus 1, and then plus 2 over x. Okay, so hopefully this helped you find the derivatives of logarithms and see how logarithms can be simplified a great deal to make really complicated functions really not that bad to take the derivative of. And so hopefully this helped, and I'll see you in the next video.